Welcome to the SuperSpine Configuration module. By the end of this module, you should be able to describe how to configure a SuperSpine architecture. A SuperSpine, also referred to as a 5-stage topology, provides scalability for large data centers. The term 5-stage refers to the maximum number of routing and bridging devices that are involved in communications within the architecture. The graphic shows a 5-stage topology where server 1 is communicating with server 311. Here, traffic from server 1 goes through a leaf, a spine for pod 1, a superspine, a spine for pod 2, then a leaf, and onto server 311. Imagine the scaling issues of port densities and bandwidth with thousands of servers. Superspines provide the ability to maintain point of delivery or pod systems, which are optimally sized, and then connect the pods together. You can refer to Juniper Pathfinder for the current list of devices that support a SuperSpine architecture. You can access this link from the reference links document in the resources section of this module. SuperSpine designs integrate with both edge routed bridging, or ERB, and centrally routed bridging, or CRB pods. The graphic displayed shows a CRB pod where the layer 3 or L3 gateway is the spine. The graphic also shows an ERB topology where the layer 3 gateway is at the leaf level. A superspine can connect to ERB pods, CRB pods, and any combination thereof. The role of the superspine is to act as gateways for the connected pods. In the graphic, the implementation shows 2 pods, each deployed as ERB systems. Each leaf in the pod provides a layer 3 gateway. The overlay network in each pod uses external BGP or eBGP. A superspine acts as routers to the spine devices in the attached pods. As a router for spine devices within a pod, the role of the superspine is to forward Type 2 and Type 5 advertisements between pods. The graphic shows a server from Pod 1 VLAN 2 communicating with a server in Pod 2 VLAN 2. This communication happens through Type 2 routes, just as it does between 2 servers on the same VLAN within Pod 1. If a server in Pod 1 VLAN 2 communicates with a server in Pod 1 VLAN 4, it would use the server's default gateway on the local leaf. If a server in Pod 1 VLAN 2 communicates with a server in Pod 2 VLAN 6, a Type 5 route is used. In the use case shown, there are 2 pods, each with 4 leaf devices and 2 spine devices. A superspine connects the pods. The underlay for the entire topology is based on eBGP, and the overlay is also based on eBGP. The Pod 1 underlay configuration is displayed here. The 2 spine devices peer with the 4 leaf devices, and the leaf configurations connect back to the spine devices. In each case, you export the loopback address needed for the overlay. The Pod 1 overlay configuration shows the eBGP group that peers to the loopback addresses of all the devices within the pod. When looking at configuring a superspine, the components will be familiar to you. First, configure interfaces to connect to the pod spine devices. Next, you establish the loopback 0 interface with an IP address used in overlay peering, and finally, configure the export policy to export that loopback interface. Configure the router ID for each of the superspine devices and configure the BGP group for the superspine underlay. The displayed code shows configuring a local autonomous system number or AS number of 65301 for superspine 1 and the peering of all spine devices in pods 1 and 2. Superspines 1 and 2 have similar configurations. For the superspine underlay configuration, you must configure the pod spine interfaces to connect with the superspine nodes and add the superspine devices to each pod's group underlay. Since the use case uses eBGP for the overlay, the AS numbers we use are 65301 and 65302. When configuring the SuperSpine overlay, start by configuring the AS number within routing options, or you can use the local AS parameter within the overlay group configuration, followed by configuring the BGP overlay group with Ethernet VPN or EVPN signaling. Set the local address to the SuperSpine Loopback 0 interface. Next, configure the neighbor peering to all the spine devices with each pod and the other SuperSpine. Then, set up the overlay BGP groups within the pods to peer with the SuperSpines. The configuration of a SuperSpine is very similar to the configuration of a pod spine. The difference being now you are peering with pod spine devices instead of leaf devices. At this stage, the SuperSpine topology has Type 2 conductivity across pods. If you require internetwork conductivity, configure a virtual routing and forwarding or VRF routing instance on each pod routing device, all the leaf nodes in this use case to advertise Type 5 routes, which the SuperSpine advertises between pods. The code shows a VRF routing instance configuration where the layer 3 interfaces for the VLANs, in this case, IRB.1 and IRB.2, are within the routing instance. The code also shows a unique route distinguisher for each device and a VRF target for importing and exporting.